Okay. Thanks for coming to the makeup lecture. One of a few that's coming up. This one is about low cycle fatigue, and it comes after our discussions of how to accommodate all kinds of different effects in high cycle fatigue. And in chapter 8, we had a lot of sort of preview and basics of low cycle fatigue. And so today we'll go a little bit more in detail and talk about how people have approached low cycle fatigue for some applications that I mentioned last time, like devices or components that just need to work for a low number of cycles, especially those that need to be lightweight, or like aircraft payloads and things, high temperature pressure vessels, or this can also apply to components that would otherwise be undergoing high cycle fatigue at kind of lower strains, but then they would have a few excursions, unexpected excursions into very high strains. And so some of the things that we'll learn about today and in the next lecture, when we do an example problem, we'll talk about the distinctions between low and high cycle fatigue in a little bit more quantitative detail, and then also how to combine or say which regime is dominating in what type of problem. Okay. So this lecture is based on chapter 11, which is a fairly short chapter, all things considered, but it has some nice details, especially about how we think about low cycle fatigue conceptually. And so in the past, we have been talking quite a bit about high cycle fatigue. Let's put stress amplitude. And we always had like an SN curve, right? And we said it only applies for like anything kind of 10 to the minus 3 cycles or above. And if it was a ferrous material or some other specific alloys, then it had an endurance limit at the end of that SN diagram. And some materials never have an endurance limit, but they keep going, and you can get very, very long life out to 1 million, 10 million, and higher numbers of cycles. And when we started the class, one thing we said was, if you don't have this SN curve, but you need it, but you have material properties, like you have the ultimate tensile strength, and you have the endurance limit, we'll call it like sigma E, something like that, then you can assemble the SN curve yourself. And what you did is you came up here and you said that whatever point we're starting at was some coefficient times the ultimate strength, like 0.8 or 0.9, and so we could do that. And so that's kind of how we've left this curve. But in reality, you can draw the rest of it, and if you draw the rest of it, it does a little curve up like this and hits the y-axis at the ultimate strength. So if I have a tensile specimen and I'm putting it in tension and equally reversing compression, if I do that up to the ultimate strength, then I should come to a limit where I only get to do that one time, right? So that makes sense with our concept of, if I pull a tensile specimen to failure, I do that and it breaks completely apart at something like the ultimate stress. So that's what we've had in the past. And it's difficult to think about the limit as n goes to very low cycles, because we get yet another inflection point in this curve, and then it comes over. And so it merits a little bit more of a detailed look at this section here, rather than using stress life and those kind of approaches to come up with something better for this section here. What happens in the cyclic stresses, as opposed to a monotonic increase in stress until there is a fracture, I mentioned this before, and I don't remember which lecture it was, but if we look at stress strain curves for monotonic stress increase versus cyclic stress increase to different levels, then we would find that there's a different curve for the monotonic one versus the cyclic one. So if we look at, these are some of the same curves that I drew before. So if we look at a material like 2024 T6, and we had the monotonic stress strain curve, it would come up, it would reach a yield point, and then it would do something like this. So that's a monotonic, right? I pull on it until it breaks. But if I do now a cyclic load, maybe it's fully reversing. For this material, it is strain hardening. So that means we get an increase in our, put some data points up here, we get an increase in our yield stress. And so we get something that goes like this instead. Okay? And so we can't apply the same things as we would in an elastic, or sorry, in a single monotonic situation to the cyclic situation. So what does this mean? Let's say we took this same material and put it in a strain-controlled experiment instead of a stress-controlled experiment. So this is just a sawtooth wave, so this would be like strain versus time. Okay, so it's a uniform strain, and we just go to the same strain levels in time, and we'll say that this is around 0 initially here. This is like a fully reversing strain. Okay. And so if we have cyclic hardening, then the stress versus time curve shows increasing magnitudes with each cycle. So this would be, as an example of this 2024 material. So if we have a 0 here, then we would come up, right? And then we would fully reverse that down to another, a strain, compressive strain, fully reverse it back up to the same level of compressive strain, but now it's at a higher stress because this is a strain hardening material or strain strengthening. And then it's going to keep doing this, going up incrementally each time. Right, so we could actually draw like an envelope here around this increase to show that it is widening. And we could again plot this on a stress-strain diagram. Right, of the actual experiment. So we would come out here and we'd go up to a certain strain. Okay, pretty straightforward. And then we're going to fully reverse this. So it's going to drop down sort of with the same slope and go back over to the fully reversing strain that we've assigned. That's not symmetric, but pretend it's symmetric. And then we go back up again to the same positive strain, except now we're at a higher stress. And then we do the fully reversing situation from there, go back to the other one, and it's slightly lower. And then we go back up again. And we go up higher, yet again up here. And then we could continue this process. And you can see that the hysteresis loops are getting sort of tighter and tighter the longer we go. So the effect diminishes. We can't get increasing strain hardening forever because we'll eventually get to high enough stresses and strains that the thing will eventually fail. But you can see these are called hysteresis loops. And hysteresis just means the curves don't lie on top of each other. The shape of the curves, if you have a reversing, let's say, input, and you look at some output curve, it's going to have hysteresis. It doesn't lie on top of itself, and the shape inside these hysteresis loops is changing. And in this case, the area is decreasing a little bit. So the curves start to collapse on themselves. We can think about these same things, but now instead of strain hardening, we could get strain weakening. So I'm going to go to a red color. And we had also a corresponding plot for steel. It goes up much higher, but it has a monotonic stress strain curve like this, right? And it has that little nose, and then it goes over like this. But the cyclic stress strain curve is lower. So this would be like for, let's say, an SAE 4340 steel. And the y-axis on this is not to scale. Steel has a much higher yield strength than aluminum. But that's the idea. And so if we have the same exact strain experiment, fully reversing strain, instead of getting increasing stresses with time, we would get decreasing stresses with time. And so we could draw an envelope here like this that would be decreasing. Right? So the material's ability to withstand the cyclic response is decreasing. Its yield strength is lower. And then if we come over to the hysteresis loop, you can see how we would draw it, but instead of starting at the lower stresses for each strain, we're just going to start high. And we'll do like sort of fully reversing to here, and then it's going to come up, but it's going to end a little bit lower. So it sort of crosses itself. This curve is getting a little bit crazy, and my hand is wobbling a little bit. But you can see now that the stresses go lower and lower. And they don't start to resemble a line. They sort of maintain their shape, but those stresses get lower and lower. So this is what the data would look like on two opposite types of materials for strain hardening and strain softening. Another way to call this would be like cyclic softening. Right, I'll write it in blue, or cyclic strengthening. So if we can have these two different types of responses, how could we possibly capture that in some sort of approach where we could capture both of these and sort of give us some engineering design rules to do this? This is where some early researchers come in, namely Manson and Coffin. We will have heard Manson's name because he had that double linear damage accumulation rule. And so he worked generally in this area. And so what this took, similar to the stress life approach, is a lot of experimental testing. So if we go to the text, and this is figure 11.5, we found that early researchers did tons and tons of experiments where they kept a plastic strain instead of plastic stress. Sorry, not plastic strain instead of plastic stress. They kept a constant strain, but they did it at a very high magnitude. So if we call this our change in strain on the y-axis here, and cycles to failure, and we really only go from, let's say, 1 up to 10 to the third, right? So we are in this low cycle regime, and we're trying to get these things to fail. So they're very high strains. They found that they could start and have monotonic fracture points, right? So that means you pull it and you don't even get one fully reversing cycle. You just pull it and it goes into ductile failure and then breaks, right? So those would be here at the beginning. And I looked at this plot and it was very funny to me because if we go from one fully reversing cycle, then you can get failures at a half, right? Because they have just gone one tensile test. And so they did many, many different materials. And when I say many, I mean different types. So aluminum, copper, stainless steel, nickel, different alloys. And what they found is that there was a strong trend. I'm not going to draw all the data points on here, but there was a strong trend like this, right? And so when you have like thousands and thousands of data points over ductile materials with different crystalline structures, and then it really is a very strong trend. Okay? Stronger than you would find for, let's say, materials in the stress, the SN diagram, right? Stress and cycles, right? So you can draw these SN diagrams for stress for all different types of materials, but the slopes are going to vary quite a lot, right? But for these types of experiments, the slopes really don't vary that much. And so they said, okay, if we're just going to fit kind of one line to all of this, and this is a log-log plot, then we'll say that it has a power of kind of minus 0.5, right, for all of these. And that turns out to be refined in this chapter, so don't take that as the gospel, but that's kind of a guideline. And so they went out to kind of 10 to the third power. And if this is low, if this is very high strains, they went ahead and said that these are plastic strains. Okay? Because what they're doing is they're putting this in an instrument and they are stretching it way beyond the elastic strain. And so if they're doing that, then they know that they're overcome the elastic strains very quickly, and they're really only in a plastic strain regime. And this kind of aligns with what we talked about very early in the class, when a component in a stress state can go from elastic to plastic, and the plastic strains are much higher than the elastic strains. Okay, so that's what early researchers did. And it caused them to want to propose a way, which is a power law expression, of expressing this relationship for any type of material such that it could be used for design. And so this is equation 11.1 in the book. This is it's called like the Manson coffin equation, right? It's very Halloween themed here, or the Manson coffin rule. And it says that if we take the plastic strain and divide it by 2, that is equivalent to a coefficient, we'll call it epsilon prime f, and then we have a power relationship with the number of cycles to failure. And we're going to have a factor of 2 inside here. With the stress life approach, we didn't have that factor of 2, but we will have it here because each cycle becomes a little bit more important now. Before we had 10,000, 100,000, whatever number of cycles. Now we have 1,000 or 500 or 200. And so these 2's can sometimes make a difference. And then we would take that quantity to some power c, where c originally was like minus 0.5. This E prime F at the beginning is a fatigue, they call it a fatigue ductility coefficient. All right, it makes sense. It's a coefficient on the power law. And it's defined as the intercept at the number of cycles equals basically 1, right? And so if this is n, then I can change, if I'm looking at this plot that I've made, I can change the x-axis to be 2, right? So it aligns with kind of our thing. And then this becomes 1 here, and this is 2. Okay. So then this becomes 2nf on the x-axis. Okay. So that means that's when this hits kind of this intercept. They call it a strain intercept at 1 load reversal. That is, this 2nf is equal to 1. So these values here, for whatever materials they are, is the E prime epsilon prime f, the fatigue ductility coefficient. 2NF is the total number of reversals to failure. So the 2 and the NF has a different definition now. So N in the past, N was a fully reversing cycle. But now each cycle matters more. So now for low cycle fatigue, we have NF, right, which is a half of a strain cycle. So that's why we always work with 2NF, right? So it's just a slightly different definition. Okay. And then C, the exponent there, is a fatigue ductility exponent. And it's the slope of that line on that plot. So this is the relationship that we have for plastic strain. And so they said, okay, this is good, but how can we now meld our understanding of the elastic and the plastic if we have constantly changing stresses and which correspondingly have constantly changing strains? Well, we're going to put it all on one diagram, but first I'm going to put together well, we'll put it all in one diagram first, and then we'll look at the equation that describes that diagram. Okay. There are 3 of these plots in our textbook, and so I'm going to kind of combine them as I go along here. So this is going to be still our reversals. So 2N is 1 reversal. So this is reversals to failure. And then on the y-axis is going to be strain amplitude. And in the prior chart, they called that like delta epsilon plastic. But we're going to try to put our understanding together here now. So if we go and look at what happens in the plastic regime, right? So we have high strain amplitude, and these are both log scales. Then we had kind of a slope that we could draw, right? That's what we had on the prior plot. But when we get out to lower strain amplitudes, we find that that slope is lower. Right, so it's something out here. And so how can we sort of put this together into something that we understand? Well, what we like to do as engineers is connect this into a single curve and talk about why it has this kind of double description here. So we're going all the way now from like, half a reversal all the way up to much greater than like 10 to the third, right? So maybe out to like 10 to the 6th, 10 to the 9, things like that. So this is our total of elastic and plastic, because when we're doing a real experiment, that's what we get. We always get the sum. We can't do an experiment where we somehow partition those unless we just stay in the elastic range. And so we can draw sort of the line that we had before. Let me draw these theoretical lines here. All right, so I'm going to draw it really close like that. So if I draw that line, that's my plastic line that I had before, right, with this expression of, I'm just going to write it here, right, delta epsilon plastic divided by 2 is equal to this coefficient times 2NF to the C. Yes. Okay. So that's our plastic region. But we have another one over here that is the elastic region, because when we go to really high fatigue, or really high numbers of cycles, like past 10 to the third, then we have that line. Okay, helpful, except we don't have an equation for that yet, right? We had some equations we used on a stress n number of cycles curve, but not on a strain number of cycles curve. But you can see now, if we sum those two, and I've drawn them very close, but if we sum those two, right, then we would get something that's much more continuous. Right, and it would be up high, right? So now we get a smoother curve, which is what we would kind of expect, right? So you could imagine that our blue curve is not really two discontinuous linear regions, but it's the sum of two lines that cross. And so what it is now we get our gradually changing line. So that better aligns with all the empirical data that was collected. So now what do we do with this elastic portion here? Well, we give it an expression that's similar to the other one, just with a different slope and a different coefficient. And so we will say that delta epsilon in the elastic region divided by 2 is equal to, we'll call it stress prime F divided by E. So before we had a strain fatigue coefficient, but it couldn't be based in elasticity because it was in a plastic super high strain regime. But now this is in the elastic regime, so this will be our coefficient. It should be anyway. And then we still have 2NF in here, so we can put on the same plot. And instead of C, we'll give it an exponent of B. Okay, so I'm going to put that on the plot right there. And then where it hits this, where it hits the y-axis should be the elastic strain. So it should be, come on, pen. It should be this sigma prime F divided by the modulus. And so this is a really good conceptual way of thinking about these things and how they sum together. If you want to think physically, a little bit more physically about what is happening at these different locations, you can think of this high strain amplitude sort of toward the left side of the plot as being like a really big, if this is our stress strain curve, right, we have these really big hysteresis loops like this, right? Because every time we reverse, we have a lot of plastic strain going on. And then as we go down into the elastic regime and the plastic strain drops off to 0, then we would have something that is much lower and much more linear like that. Okay. So if you were looking at the experiment and you were thinking about the stress and strain, that's what that would look like. And then in the middle, it's something in the middle. Okay. And so let's talk a little bit about where these cross. Okay. So if we look at where these two cross, right, we can follow that down and then say that this is some sort of a life here on the x-axis that is the transition life. How many cycles can we do, or how many cycles will it last at a particular strain amplitude where it's going to be very low, and we care more about the strain and the ductility, or is it going to go into this higher cycle regime, which is still more elastic, and now is focused on tougher materials would be better. Okay? So this gives us sort of a design criterion. So if we know what our strain amplitudes are going to be, and maybe we're given a strain amplitude spectrum of loading or something like that, and we need to pick a material, well, if we need to have a lifetime that's very low, or we can have an allowable lifetime that's very low, then we're going to pick a material, and I'm going to write the name, like I'm going to write this on the left side here, even though this plot's getting super busy. I'm going to write it here, right? We want a material with a very high strain to failure that is very ductile, right? So we want something with high, let's maybe strain strengthening or something like that. because we know that we are going to be making use of that ductile regime because we have a lot of plastic strain compared to the elastic strain. But if we're on the other side of that transition life, we might want to choose a material with a higher toughness because we have more elastic strain compared to the plastic strain. We're kind of in a transition regime where it's not completely elastic. We can't use linear elastic fracture mechanics, but we're also not in this low cycle fatigue completely. So we're kind of in a gray area. So we use low cycle fatigue analysis, maybe try to partition the strain and see where we're at. But if we want to be in that regime where it's past this transition lifetime, we really want to choose a tougher material there. Okay, so then we can put the equation together. I'm going to put it on the next slide. And this is equation 856 in the textbook. So they do present it in chapter 8, even though they don't describe it much in detail. And then I forget what the equation number is in chapter 11, but it's the exact same equation. 11.2? Okay. It's also equation 11.2, and all it is just a summation of those two. So the strain amplitude divided by 2 is equal to the sum of the strain amplitudes in the elastic and plastic regimes. All right, so we'll have in the elastic regime sigma prime F over the modulus 2NF to the B plus our strain fatigue coefficient 2NF to the power C. So it's basically like so it's a summation on a log-log scale, which is a superposition of two power functions like that. Okay. There's a nice discussion in the textbook also about choosing materials and whether you want high strength and high ductility or whether you want higher fracture toughness. And so because we have those two, those are not necessarily correlated. And I found a very nice chart to show you, how these things might play together. So if you've taken courses with material selection or anything like that, you might have seen these types of charts. These types of charts are called Ashby charts. After the engineer from the UK, and he came up with all different kinds of these charts based on designs for different types of things. And what they do is they pit two material properties against each other. And so on this plot, you can see on the x-axis here is fracture toughness. Okay? So this is really what's going to guide our thinking about stress life and more if we have more elastic strains. And then on the y-axis is yield strength. So we really want high strain to failure and high yield strength, but there's no Ashby chart for strain to failure. So we'll use this one. And so the chart itself is not new. So this is from a research paper, and it's here on the slide. So when I upload the slides, you can look at it. But I found this chart to be very helpful. Not necessarily the entire paper, but yield strength is on the y-axis, and so it gives in the different colors different classes of materials. So the purple one, medium carbon steel, the yellow one, high carbon steel, aluminum alloys is at the bottom, kind of in a dark pink, and then on the top left, you can see red, which is tungsten carbide. That kind of always anchors a lot of these Ashby charts. Tungsten carbide is like a very, very hard material. It's used on cutting tips for machining and things like that. And then next to it is like silicon carbide, same thing. Okay? So this is all ductile materials, steels, aluminums, tungsten carbide, which is a ceramic. And so all of the ductile metals are kind of on the bottom right, ceramics on the top left, but many different material classes here. And what this paper is about is different regimes where you can use different types of failure analysis. So I thought this was very fitting. So what they've done is they've put these dashed lines on top of the Ashby chart. And these lines do not represent, they do not represent a ratio of, let's say, yield strength to fracture toughness that you would want in, I don't know, an antenna or whatever, or a chair leg or some component, right? That's what we normally would use Ashby charts for. But what they've done is they've put these materials and combined them into simulations, and then identified which regime would be used based on a plastic zone size calculation, right? So we can do this as well, right? We've been looking at in Chapter 8 some expressions for what is the zone of what's the plastic zone size around a crack tip. Okay? And so if we have super, super hard materials, let's say you're up in your ceramics here, your tungsten carbides and things, they have a very high yield strength but low fracture toughness. And we always use linear elastic fracture mechanics for those types of materials because they really don't have any plastic regime. Okay, so here they've described the plastic zone sizes are almost like negligible, right? Like 0.005 micrometers is 5 nanometers, which doesn't even make a lot of sense since it's about a few times higher than atomic spacing. And so I might argue with their number and being included in here. But as you go up into the ductile metal regime, you see now that plastic zone size is on the order of tens of microns. So this could be a small grain in the material, or it could, something like that. So it's on the size of getting to the continuum level, which is where all of this stuff kind of applies. And for that, they say you can use a micro EPFM, elastic plastic fracture mechanics. So that's kind of what we've been talking about here. And then as you go to materials that have a much higher fracture toughness compared to their yield strength, then you can use macro scale EPFM. So you still have kind of medium yield strength here, but you have a lot more ductility. And so this is kind of what they observed in the paper, right? And so you can see now how the regimes of what you want in a material relate to this. As I'm looking at it now, let me just look at this for 1 second. The plastic zone gets bigger as the materials go. Okay. Yeah, up in fracture toughness versus the yield strength. So higher yield strength materials, okay, this is making sense, yes. Higher yield strength compared to fracture toughness is going to lead us down to those smaller plastic zones and linear elastic fracture mechanics, right? So sort of the top left going up and top left, right, is sort of our high cycle stress type regime we're looking at. And then in the lower right is the opposite. In the lower right, we really need to include the plastic fracture or plastic strain considerations. Okay. So we only have a couple of minutes left, so I wanted to close with some empirical relations that the book gives us for these exponents of the equation that we were looking at. Let me go back here. Okay, so I had ended before on this slide where I gave this equation which makes use of the Manson-Coffrin rule in the plastic regime and then adds on an elastic regime such that we can sum them. And so really, we're really out in like experimental, empirical land now. So it says in our book, typically B ranges from minus 0.05. So that must be sort of an extreme type material, up to minus 0.15. right? So that had a lower slope. This is the high cycle elastic strain exponent. And C is higher than that, which makes sense according to our graph. So that can be, oh, that's funny. I have these switched. Hang on a second. Just change my little inequalities here. Okay. And then C is between about minus 0.8 and minus 0.5. So they thought initially it was all kind of minus 0.5, and they found some other materials. Okay. When we have been doing this, it might make sense to go back and think of what we had before when we talked about strain hardening. When we were talking about stress, we had this equation which was our on the, I didn't write this down, which is a bad move. We had a strength exponent, right? So we had, we're fitting strain hardening. We had this exponent n prime, right, which was a cyclic strain hardening exponent. And this is like way back in like chapter 3. So it would be helpful if we could use that same strain hardening exponent use it and see how it relates to these exponents here, so that we don't have to be looking up B and C and N and S and all of these things. And so what researchers did is they approximated these according to these relationships. So B is going to be equal to minus n prime divided by 1 plus 5n prime. And C is going to be equal to minus 1, so it has the same denominator but a different numerator, divided by 1 plus 5 to the n prime. So if we have this cyclic strain hardening exponent from unidirectional tensile testing, then we can put it in here, and if we prescribe a specific strain magnitude, then we can, we done? Strain magnitude, then we can partition that out into elastic plastic. All right, so we'll end there for today, and pick back up on Tuesday, where we will finish. There's just a couple more concepts in the chapter: influence of non-zero mean stress or mean strain, and then we'll do an example problem in which the component has to last for 15 minutes, which I thought was a really fun example problem. Okay, so see you guys later.